So in this class, we're going to talk about uniform integrability. So in the last class, we mentioned a lot convergence of martingales, and I'll start motivating the study of uniform integrability with an example coming from the convergence of martingales. So it's no coincidence. Uniform integrability is very useful in the study of martingales and their convergence. So let's start with an example that we mentioned in the last class. So suppose that xn is a simple random walk. So I've defined this in the last class. And let us also define a stopping time t, which is the first time in which, so this is a simple random walk starting at 1, and the first time it hits 0 is called t. So we had a picture in the last class which goes like this. And this is the time t we are talking about. So we also defined yn to be actually the integral of x with respect to h, but there's a simpler way to define this, which is just xn minimum t. So when n is smaller than t, we're going to follow xn, but as soon as we hit t, we get stuck there. So the process y is going to follow x through its trajectory until time n, when it remains at 0 from then on. Okay, this is yn. So why are we coming back to this example? So the reason is very simple. The yn has a bit of a strange property. So we know that yn converges almost surely. Actually, it converges to 0 almost surely. So we know that for every omega in our sample space, there exists a random time t, which is finite almost surely, such that this is exactly the same t, such that yn is equal to 0 for every n bigger or equal than t of omega. Okay, so this is an interesting property of this process y, that it converges to 0. But we also know that yn, being the integral of a martingale, is also a martingale. And in particular, we mentioned this in the last lecture, the expectation of a martingale is the expectation of the conditional expectation of this martingale given fn minus 1. This is what is inside here is exactly yn minus 1, or almost surely yn minus 1. And we can continue this calculation, so on and so forth, until we get the expectation of y0. So a martingale never changes its expectation. And what is y0? y0 is 1, right? So this process here always has expectation 1. So how could it be that it converges to 0? Know that expectation of yn on the one hand is 1, but that's definitely not converging to the expectation of the limit in n of yn, which is 0. So this is an interesting property. It is not the first time we see a sequence of functions that converge, but the expectation do not converge. So let me give another example, not in the martingale context. So if you take a sequence of functions Zn from 0, 1 to R that has the following formula, Zn of x is equal to n times the indicator of 0, 1 over n. So this Zn converges to 0 almost surely with respect to the Lebesgue measure. But the expectation of Zn is 1 always, which is different from the expectation of the limit, of course. So this is not a big surprise, what's happening with the process y here, but it's definitely frustrating. We would like to have some hypothesis under which we know that not only y converges, but the expectation also converges. So when can we say that? For example, if yn converges in L1. So if yn converges not only almost surely, but in L1, then the expectation of yn will also converge to the expectation of the limit. So in this class, we're going to talk about uniform integrability, which is a subject very much related to these translations of convergence. Can we take something that converges almost surely and prove that it converges in L1? So this has been the motivation. Now let's jump straight into the definitions. So suppose that we have a family of random variables x alpha. So alpha is a potentially uncountable collection. So this is a family of random variables. So we say that x alpha is uniformly integrable if the supremum over alpha of the expectation of the absolute value of x alpha on the event that x alpha is larger or equal to m converges to 0 as m goes to infinity. So I know this is a long definition, so we're gonna give examples and talk a bit about the definition until we get some intuition behind it. But this is the definition. It's saying that the large parts of x are uniformly integrable, that's where the name comes from, over the family alpha, the family gamma. So let us give some examples to train our intuition. So the first example is simple. Take a single variable x in L1 and let's look at the family that has only this variable. So now the supremum in alpha that appeared here is not gonna show. There's only a single variable. And the expectation is gonna look like this. Indicator that x is larger or equal to m. We would like this to go to 0 as m goes to infinity. Let's make a intuitive graph here. So let's imagine for now that this is our state space and x is a variable taking values here. Maybe it blows up, I don't know. If it's uniformly bounded, then this is going to be 0 for some value of m. So we're going to take a variable that is not uniformly bounded, like the plot there. And what we're doing is we're taking a value m and only integrating x where x is bigger than m. So we're taking the integral in this region here. And we want this to go to 0. Actually, it's not hard to see that since x is in L1, all this sequence here, we can see this as a sequence of random variables that we call ym. So ym is bounded by x for every m. So this means that it's dominated by an L1 function. So by the dominated convergence theorem, the limit as m goes to infinity of this is equal, by the dominated convergence theorem, to the expectation of the limit as m goes to infinity of ym, which is, so what is the definition of this limit here? It's going to be infinity at x equals infinity. Why? Because if you are in this set here, then you're going to be in all these sets here, and this is going to be equal. And if you are outside the set here, then you are outside, you're going to be outside one of these sets here for m large enough. So after that m, you are 0, just as in down here. So this is equal to the limit of ym. But remember, if x is in L1, then x equals infinity has probability 0. So that means that this is exactly 0. So we showed that this limit in m is 0. Therefore, the family that only has the variable x is uniformly integrable. Okay, so this is similar in spirit to the conclusion we had in the earlier parts of the course, that a single distribution is tight in a Polish space. And now we're going to give a second example that also has some connection, intuitive connection to previous results. If we have a finite family x0, x1, xk, where xi is in L1 for every I, is also uniformly integrable. So not only a family with a single random variable is uniformly integrable, but finite families like this are as well. I'm not going to give the full proof, you can try it yourself, but just observe that this limit is 0 for each one of them. So the limit of the maximum also has to be 0, right? So there's not much to be proven there. Okay, of course, we are interested in infinite families, right? Because we are going to use the uniform integrability on sequences that are converging. If the sequence belongs to a finite family, then the sequence is going to be quite boring. So we're interested in infinite families and their uniform integrability. The next theorem is the first non-trivial example of an uniformly integrable family. So suppose that P is a parameter larger than 1. Okay? And let's take a family X alpha, not necessarily bounded, not necessarily countable. And let's assume that the expectation of x to the alpha, x alpha to the p is smaller or equal than k uniformly over alpha. Okay, so we have a uniform bound on the p moment of these variables. So then the family is uniformly integrable. Okay, how do we prove this? So let's start with the expectation above. We can, since we assume that p is larger than 1, we can break this expectation in this variable inside the expectation in two terms, x alpha and x alpha, to the p minus 1. This always makes sense. And it's interesting to note that, if x is large, this is also large, because even if it's raised to a small power, this power is still larger than 0. So in more precise terms, if x alpha in absolute value is larger or equal to m, then the right hand side there, x alpha to the p minus 1, is going to be larger or equal than m to the p minus 1, which goes to infinity. So we can lower bound what's above by m to the p minus 1 times the expectation of x alpha on the event that x alpha is larger or equal to m. So what did we do here? We started with this expectation and we multiplied by this indicator function. On this event, right, we know that the right term here is larger than m to the p minus 1. That goes out of the expectation. And another way to write this is to isolate the right hand side here. This is actually what we are interested in when we're talking about uniform integrability, right? And we just showed an upper bound on this, which is great, right? It's exactly what we are looking for, over m to the p minus 1. And we've seen, by hypothesis, that this expectation here is uniformly bounded. The p moment is uniformly bounded by k. And this goes to 0. This holds true for every alpha, right? It's just we are just using a bound here that is uniform over alpha. Look here. So since this holds for every alpha, the supremum over alpha of the above expectation is also smaller or equal than k over m to the p minus 1. That goes to 0 with m. So we've just proved that the family is indeed uniformly integrable. So in the next class, we're going to see other examples of theorems similar to this, but you see that this theorem is somehow a bit strong, right? We are assuming that the variables have a moment larger than 1 that is uniformly bounded. I will leave it as an exercise here to show that this is not necessary. For example, if the expectation of x times log of x alpha is uniformly bounded, we can also prove that the family is uniformly integrable. But the problem is that we really want to get rid of any extra factor. We would like to say that if the family is bounded in L1, then it's also uniformly integrable. But this is not true, right? So we can find examples of a family X alpha such that the expectation of the absolute value of X alpha is smaller or equal than K uniformly over alpha, but X alpha is not uniformly integrable. We are not. So how can we? Let us give straight away this counterexample. We already wrote it here. It's our family Zn. So Zn that we have defined here is a family that it's positive, right? All these guys are positive. So the expectation of the absolute value is also 1, so it's also uniformly bounded. But let's see that this is not a uniformly integrable sequence. So let's go down here. So we're going to, in fact, Zn is such an example. Why? Let us calculate the expectation of Zn on the event that Zn is larger or equal in absolute value to m. Okay, so let us plot what Zn looks like, right? It's a function from 0 to 1, and it is only different from 0 up to 1 over n. And in this interval, its value is equal to n. So if n is larger or equal to m, then this expectation is exactly equal to just Zn. Why? Because Zn is bigger than m exactly where it's bigger than 0. So this is equal to 1. We already know. So if we're integrating z only in the region where it's bigger than m, when n is bigger than m, this is just the same as integrating z, which gives us 1. So that means that the limit as m goes to infinity of the supremum over n of the expectation of Zn at this event is what? Fixed m, this supremum is gonna have values where n is larger than m. So this is bigger or equal than this, which is 1. So the limit is different from 0 because we have infinitely many values for which the supremum is bigger or equal to 1. Okay, so indeed we cannot simply remove all the fat here and say that if a family is bounded in L1, then it's uniformly integrable. We're going to try to see the closest relation that uniform integrability has with convergence in the next class. So see you there.